All right, folks, welcome back. It is good to have you. And in this video, I'm going to talk about something that I see as a common problem among people who are just kind of getting started, getting their feet wet with data modeling. They focus too much on accuracy and feel that a model is somehow a disappointment when its accuracy is lower than they expect it to be. And they often think either it must be lower because of either something they're doing wrong or because of something they weren't taught or weren't shown. And that's not necessarily the case. There might be times when different variables, different inputs, transformations could change accuracy. But what I want to focus on here is situations in which that's not the case. So without further ado, I'm going to jump to the next slide where you'll see those 5 things that I want you to think about. So when you see an accuracy value that you don't feel good about, I want you to think about this first point, which is listed as the top one here, and I think it's the most important. What are the natural limits to accuracy based on this data and this problem? And let me explain what I mean by that. Suppose we were trying to make a predictive model in which we could try to understand the ratings of Uber drivers. Well, I've asked lots of people about this. I've asked people, what makes you give a particular rating to an Uber driver? And I get a pretty standard set of answers. People will say, did the driver drive safely? Was the route direct? Did I get to where I was going on time? And then they'll offer some more subjective things like, did the car smell okay? Was the driver creepy? I've certainly heard that one a few times. Or did the driver talk too much or too little? A lot of other things can sort of factor into this. So then I'll ask them, I'll say, well, let's think about data that we could easily collect. Let's think about objective data that we could have, what we could imagine in a data set if Uber were to grace us with this data. What are some things that we could know and that we could store in a nice, happy, rectangular CSV? And students will say things like, well, we could know things like the age of the car. We could know how many trips the driver had taken. We could know how long the driver had been on shift that night or that day. We could know how long the driver had been with Uber. There's a lot of things that we could know objectively that might help us. But then if you think back to the things that actually cause people to deviate with their ratings, those are not things that would be easily capturable in a data set. We're not going to have a data set with some static variable that's, does the car smell okay, right? That's just not something that we would have there. And there wouldn't be a variable for creepy with a simple yes, no, or even with a numeric score. So there's going to be there would be huge limits on trying to make that prediction. Anything else, especially anything involving people. I've seen this come up. One time I remember working with students on a restaurant tipping data model, and we got pretty good. I think we used a classification tree after binning up the types of tips based on their relative size to the bill. And a student said, well, but how come we can't get it better? Like if we knew more, we could somehow achieve an even higher accuracy. Why can't we get this to be 100% accurate? Well, wait a minute. We're talking about a decision that people make that is not subject to scientific laws. Someone's decision on how much to tip could be very subjective. It could have to do with how good of a day they had, how bad of a day they had. Maybe it has to do with how easy the math is based on the bill. There's a lot of things that could impact accuracy there. And so you always have to do that. And that's not something that a book is going to teach you. It's not something that's going to be knowable just by looking at the data and the numbers. You have to just think about the domain. What are you studying? If you're looking at a consumer to consumer type of commercial model, you're looking at something like Airbnb rental prices, and you're going to predict those with linear regression. Think about why that's a very, very different task than, say, predicting hotel room prices, okay? Because in the first case, you're subject to these very arbitrary decisions people might make. Hotels are competitive businesses. Not every Airbnb tenant is in a competitive business or would feel like they are, and that can impact their pricing decisions. Okay, so I'll move on from that, but that is just so important. And like there's a note here at the bottom. I want to keep this moving. but I want you to know every one of these could be its own topic, and it should be, and I plan to make a separate video on each. Okay, number 2. Can this model do something else? Okay, so we get it. Accuracy is not sky high. Can it predict a rare outcome class? Okay, we may not care about accuracy. To use an example I sometimes go to in class with my students, if we were selling luxury yachts, each one of these things is worth millions of dollars. Every time someone buys one, we are going to book millions in revenue. So if we just want it to be accurate, well, we could just apply the naive rule. No one ever buys one. Okay, great. Well, we can be real proud of ourselves. Well, our accuracy might be very close to 100%, but we've done something that's functionally useless. And there's a lot of other examples like that. We could always just predict that there's not credit card fraud. In other words, we could predict that every credit card transaction is legitimate, and we'd be actually pretty darn close to 100% correct. But that wouldn't be the purpose of the model if a bank or a payments transaction company was tasking us to build it. They might be much happier with a model with lower accuracy but more functional use because it actually identifies that rare outcome class. So those other topics there, those are things I'd love to make separate videos on, terms like sensitivity, precision, specificity, F1 score. That's all for another day. But that is so important as well. Okay, number 3, this is something people don't often think about doing, but when you are using a modeling system, let's look at, say, logistic regression or naive Bayes, just to name 2. Behind the classification outcome prediction, there is a numeric probability associated with membership of that record in either the 1 class or the 0 class. So we can, by default, the algorithm is going to use 50-50 because that is a natural default. That is a natural cutoff to say, is it or isn't it? But what we can do, it's perfectly legal, it's perfectly within the rules of the game as long as we disclose it. We could just say, we are going to only make the predictions when the model's number is above a certain number or below a certain number. So to use the numbers here on the slide, what we could say is, if only when we have a predicted probability of 0.8 or greater are we going to say, yes, we think this record is going to belong to the 1 class. And only when that is less than 0.20 are we going to say it'll belong to the 0 class. And we can just say everything in the middle, the model was inconclusive. It's not making the prediction. And that's fair. I mean, we couldn't then just brag about our accuracy without disclosing that, but we could say that it just gives an inconclusive result in everything that falls inside that range. And that could be really special because what it could do, it can turn the business's focus. And let's imagine this is being done for a business and we're looking at something like customer retention. Well, we can say that we might do the opposite actually. What we could do then is we can look at if the people are above 0.8 or less than 0.2, we might actually ignore them and just focus on the people in the middle because those are the people who are actually on the fence. They might stay, they might go. When we can do that because we think the model's really accurate on those other ones and there's less room, there's less sort of chance of things changing. Alternatively, we could say that if we're interested in something like students dropping out of school, we could say we're only going to focus on students who the model predicts are 0.8 or higher. I mean, I could just keep going with examples, but I'll leave it there. This is definitely something I want to return to. It's very underrated. It's very useful. Okay, number 4. Is this an overall valid model that teaches us about particular variables? Here's what that means. Let's look at linear regression for a moment. R squared, a very misunderstood statistic in linear regression, and I don't know where the idea came from among people that linear regression models need to have R squared values of like 0.7 or higher. I think that's a very good thing to say when you haven't done a lot with linear regression models, and you spend a lot of time around them. You might not say that, but I want to say that let's forget about that for a moment. Let's imagine we have a model. And you're looking at the R squared, and it's 0.32, it's 0.41, it's 0.297. Okay, right off the bat, that doesn't necessarily signify any problem. It just tells us how much of the movement in the outcome variable is explained by our inputs. That's all it does. But okay, enough about that for a moment. Let's think about what we can still get out of that model, even when we are not falling in love with our R squared. If we have significant, well, first we can use the F-test to tell us, is the overall model significant? Okay, and then if we check that block, we can look at individual predictors. And we can say that, hey, I've got some really awesome p-values here, and I can connect the dots between their values and the outcome in a statistically significant, meaningful way. Even though the overall model is not doing wonders in terms of its tightness, you could say, with the movement in the y variable, there's still a lot we can learn here. That's also true in other contexts. So if you looked at variable importance in a random forest model, you could use that to tell you, well, which of my variables are really separating my records into outcome groups. And just that fact alone is valuable. That fact alone might tell you, and I'll go back to customer retention, these 5 variables are impacting retention. These other 7 variables that we thought were really aren't as meaningful. And then you can zero in on those. So that's something that needs to be thought of as well. And then finally, multi-class. And technically, 2, I guess, is multi, so that's more than 1. But I really want to say more than 2 outcome classes here. So this is something that always trips people up, because if we are thinking about binary outcome classes in which the groups are more or less balanced in the data set, then we're going to think in terms of 50-50. What do we expect our accuracy to be, and when would we be reasonably happy with the accuracy we got? But let's imagine a multi-class scenario. Let's imagine we have taken a numeric variable, we have binned it in a responsible way, putting approximately a quarter of the records into each of 4 outcome classes. Well, now the naive rate of accuracy would be about 1 in 4. And if we were randomly guessing, maybe by throwing darts at a wall, blindfolded, first we'd say, why are we doing that? But then once we got done asking, we'd realize that we were accurate about 1 out of every 4 times. So if the model is accurate 52% of the time, or even 39% of the time, that should be framed back against the naive rate. We should remember that what we're attempting to do when we start going beyond, and we start going way beyond 2 outcome classes, our accuracy expectations need to be tempered by that. So that is it. That was what I wanted to cover here. And like I said, I can dive deeper into any of these. Leave any comments that you think are relevant to this, your experiences with it. And if there's anything that you want to see more content on in particular, just let me know. And have a great day. Thank you very much for listening.